Welcome students. This is our 7th video. We shall continue with the lesson number 3, Force and Pressure of Standard 8. Today, very first topic for us is atmospheric pressure. The atmospheric pressure. Air surrounds the earth from all sides. This layer of air is called atmosphere. The atmosphere exists to about 16 km height. It further extends up to about 400 km in a very dilute form. The pressure created due to air is called the atmospheric pressure. See the diagram. Imagine that a very long hollow cylinder of unit cross-sectional area is standing on the surface of the earth and it contains air. Weight of this air is the force applied in the direction of the center of the earth. This means that atmospheric pressure is the ratio of this weight divided by the area of the surface. The air pressure at the sea level is called 1 atmospheric pressure. Air pressure decreases as one goes up in height from the sea level. 1 atmosphere is equal to 101 into 10 raised to 3 Pa is equal to 1 bar is equal to 10 raised to 3 millibar. 1 millibar is equivalent to 10 raised to 2 Pa hectopascal. Atmospheric pressure is specified in the units millibar or hectopascal. The atmospheric pressure at a point in air is equal from all sides. How is this pressure created? If air exists in a closed container, the air molecules in random motion continuously heat the walls of the container. In this interaction, a force is exerted on the walls of the container and pressure is created due to this force. We constantly bear the atmospheric pressure on our heads. However, the cavities in our body are also filled with air and arteries and veins are filled with blood. Therefore, we do not get crushed underwater and due to atmospheric pressure. As the pressure is balanced, the Earth's atmospheric pressure decreases with height from the sea level as shown in the figure. Use your brain power. At the sea level, the atmospheric pressure 101 into 10 raised to 3 Pa is acting on a tabletop of size 1 meter square. Under such a heavy pressure, why doesn't the tabletop crumble down? Think, children. Atmospheric pressure is not a force, it's a pressure, meaning it acts like a force distributed over an area and acts normal to the surface of our bodies. Though atmospheric pressure at the sea level is acting on a tabletop of size 1 meter square, the tabletop doesn't crumble down as the top has internal equalizing pressure which prevents it from collapsing. Next topic for us is buoyant force. Let's do one activity, student. Take a plastic bottle and fix the lid tightly. Now place it in a water and see. It will float on water. Try and push it into the water. Even when we push, it continues to float. This experiment can also be done with a plastic hollow ball. Now fill the bottle with water to the fullest capacity and close the lid and release in water. The bottle will float inside the water. Why does this happen? The empty plastic bottle floats on the surface of water. On the contrary, the bottle full of water floats inside water but does not go to the bottom. The weight of the empty bottle is negligible as compared with the weight of the water inside. Such a bottle with water neither floats on the surface nor does it go to the bottom. This means the force due to gravity acting downward must have been balanced by an opposing force in the upward direction on the bottle filled with water. This force must have originated from the water surrounding the bottle. The upward force acting on the object in water or other fluid or gas is called buoyant force. Again I repeat, the upward force acting on the object in water or other fluid or gas is called buoyant force. Look at this picture. The arrow pointing downward is the force of gravity, whereas the arrow pointing upward is the buoyancy force or buoyant force. While pulling a bucket from a well, the bucket full of water immersed fully in water appears to weigh less than when it is being pulled out of water. Why? Why, student? This is happens because when the bucket is in water, it experiences an upthrust in the vertically upward direction. Therefore, we can easily pull it when it is in water. But once it is out, there is no upthrust, and now there is only one force which is pulling it up. This is muscular force. Try this. Take a piece of thin aluminium sheet and dip it in water in a bucket. What do you observe? Now shape the same piece of aluminium into a small board and place it on the surface of water. It floats, isn't it? Why does this happen, students? In first case, the volume of water displaced is equal to the volume of aluminium sheet. Since the density of aluminium is more than that of water, the thin sheet is not able to displace enough weight of the liquid to stay float. In second case, the board displaces a volume more than the volume of the metal plate. In this case, it is possible that the weight of the extra volume of the water displaced can be equal to the weight of the metal, and hence the board floats. An iron nail sinks in water, but why does the massive steel ship floats on it? When an object is deep in a liquid, a buoyant force acts on it, and hence it appears that the weight of the object is reduced. It becomes easier to swim in sea water than in fresh water. This is because the density of sea water is higher than the density of fresh water due to salt dissolved in sea water. Buoyant force depends on two factors. First one, volume of the object. The buoyant force is more if the volume of the dipping object is more. Second factor is density of liquid. More the density of liquid, more is the force of buoyancy. Now next topic is Archimedes principle. Let's do one activity. Take a long rubber band and cut it at one end. At one of its ends, tie a clean washed stone or 50-gram weight as shown in figure. Now hold the other end of the rubber band and make a mark there. Keep the stone hanging in air and measure the length of the rubber band from the stone to the mark made earlier. Now take water in a pot and hold the rubber band at such a height that the stone sinks in it. Again, measure the length of the rubber band up to the mark. What is observed? This length is shorter than the earlier length while dipping the stone in water. Length of the stretch rubber gets slowly reduced and is minimum when it sinks completely. What could be the reason for a shorter length of the rubber band in water? When the stone is sunk in water, a buoyant force acts on it in the upward direction. The weight of the stone acts downward. Therefore, the force which act on it in the downward direction is effectively reduced. How much is the magnitude of the buoyant force? How much is the magnitude of the buoyant force? Is it the same for all the liquids? The answer of these questions are embodied in Archimedes' principle. This principle states that when an object is partially or fully immersed in a liquid, a force of buoyancy acts on it in the upward direction. This force is equal to the weight of the fluid displaced by the object. Introduction to the scientist. Archimedes was a Greek scientist and a mathematician with sharp intelligence. He found out the value of pi by numerical calculations. His knowledge of levers, pulleys, wheels in physics was useful to the Greek army in fighting against the Roman army. He became famous due to his work in geometry and mechanics. When he entered a bathtub for taking bath, he discovered the above principle by observing the overflowing water. He came out in the same state, shouting, Eureka, Eureka, meaning, I found it, I found it. The use of Archimedes' principle is very wide. This principle has been used in the construction of ships and submarines. The instruments such as lactometer, hygrometer are based on this principle. Lactometer purity of milk and hygrometer measures humidity. Thank you, children.